This is video 1 for group theories in music. So we will begin with the area that we'll be working in, which is abstract algebra, specifically with group theory. The objectives of this presentation are to identify symmetries in music, to use group theory to describe the symmetry in music, to give a musical interpretation of Cayley's theorem, and to apply Burnside's lemma to tone rows. So we must first begin with describing what a group is. So the definition of a group is closed, which means that for every A and B that belong to G, A and B multiplied together also belong to G. A group is also abides by associativity, which is when A times B times C equals the same thing, A parentheses B times C, for all A, B, and C that belong to G. A group also has an identity, which means that there's an element E which belongs to G such that A times E equals E times A, which equals A, for all A that belongs to G. And a group also has inverses, which means that for each element A that belongs to G, there is an element B that belongs to G such that A times B equals B times A, which equals the identity. So what are some examples of a group? We have the group Z, which is all integers, and we have Z divided by N. So as a brief background, we have to also describe what symmetry is. And for this presentation, symmetry is going to be defined as undetectable motion. So here are some examples of symmetry in music. So the first symmetry type is called translational. And in mathematics, that is identified as all the integers. And in music, it's represented with repetition. The second type of symmetry is horizontal, which in mathematics is described as integers Z divided by 2. And in music, it is seen in inversions of a figure or a phrase. So if we were to go to the piano, for an example, if we had the interval C and E, and if we were to invert those 2 times, so then we would then have E and C, and going back one more time to C and E, you can see that this would correlate with our definition of symmetry, meaning that we would not have essentially detected motion because C and E is the same thing that we just determined. So the next type of symmetry type is glide reflection. In mathematics, it's seen in the group of integers, Z, and in music, it's reflection with a displacement in time. The next type of symmetry is temporal reflection. In mathematics, it's the group Z divided by 2, and in music, it would be seen as ascending and descending scale. So simply, on the piano, if we had the scale C, however, where you see the symmetry would be on manuscript paper. So if the scale was written out from the C, the first C, ascending, and then all the way descending, if you were to draw an imaginary line on the highest C, and then you reflected it over that line, we would have symmetry. And then the last type of symmetry is rotational. And in mathematics, that's seen as in the group Z divided by 2. And in music, you will see that in a melody centered at one single note.